Hi, thanks for listening to our presentation on extractive memorization in constraint sequence generation tasks. My name is Vikas Ronak. I'm a research scientist at Microsoft, and this is joint work done with my colleague Arul. So it is now well known that neural networks capture regular patterns in the training data while simultaneously fitting noisy and atypical samples using brute force, which is what we loosely refer to as memorization. For constrained natural language generation tasks such as neural machine translation, which rely heavily on noisy web crawl data for training high capacity neural networks, this creates an inherent reliability problem in that these models can fail catastrophically on certain inputs despite very high average case performance. And while memorization has received much attention as a privacy threat, in this paper we want to characterize its reliability threat for constrained sequence generation tasks such as MT. There exist two key algorithms to elicit memorized samples, each yielding a distinctive definition of memorization itself. The first is the counterfactual definition, which checks model behavior with respect to the inclusion or exclusion of a specific sample during training in order to allocate a memorization value estimate to that specific sample. And the second is extractive memorization, which is the focus of this paper. We define extractive memorization as exact training data generation under insufficient context and propose an algorithm to elicit memorized samples from a trained model. Here's an example of an instance elicited using the extractive memorization algorithm proposed earlier when applied to a strong transformer big English to German system trained on WMT20 data. And fundamentally, the effect here seems to be that for this memorized input, the translation becomes invariant to the suffix after a certain threshold. So if the suffix is perturbed in this instance, the translation remains the same, while perturbing the prefix yields a different translation. To characterize it further, we find that the quality and diversity of memorized samples is worse when compared to the average, where quality is measured through Comet QE, which is a quality estimation metric, and diversity is measured through type to token ratio. We also find that the percentage of samples memorized is higher for repeated training samples compared to samples present only once in the training data. However, this is highly data dependent in the sense that if you have multiple unique templatic sentences which are repeated only once in your training corpus, then also you are going to elicit a number of memorized samples which are present with repetitions equal to 1. Further, to understand how the memorization of an input corrupts the samples in its neighborhood, we generate new source sentences in the vicinity of the memorized input through perturbations and test whether they generate the same output under greedy decoding. We find that in about half the cases, the translations of the new inputs are invariant to suffix perturbations, demonstrating that memorization corrupts the translation of sequences in the neighborhood of the memorized input as well. We also find that perturbing the prefix forces the model to change the output, and this implies that the prefix is being used by the model in order to trigger memorization. So we can leverage this fact in order to generate non-memorized outputs from the same model by perturbing the input prefix of the memorized samples. We design a simple prefix perturbation based algorithm to elicit non-memorized outputs from the same model. We find that for about 65% of the memorized cases, we can generate a non-memorized output from the model using this simple algorithm. The generated non-memorized outputs have higher quality and diversity, and they can be used to directly fine-tune the model in order to mitigate memorization. Finally, we show that the memorized samples extracted from system A can be used to attack a disparate system B. The success of such an attack signifies spurious correlations which could be easily learned from the underlying data distribution, and which point to shared vulnerabilities in such systems. For example, here a memorized input from our WMT20 system is used to launch an erroneous attack on Google Translate. So this is the memorized instance, and here's the erroneous translation. So to summarize, our contributions are as follows. We proposed a new algorithm for extractive memorization in constrained sequence generation tasks. We quantitatively characterized memorized samples in neural machine translation in terms of their quality and diversity. We developed a perturbation-based memorization mitigation algorithm that can be used to directly fine-tune the model in order to get rid of the memorizations. And finally, we demonstrated that memorized samples obtained from system A could be used to attack disparate systems as well. Uh, there are many new questions open for further research. Our code is available on GitHub. And thank you for listening to our presentation.